So in today's lecture, we will discuss about rates of change. We'll begin by considering a function f of x. So let us say that this function is equals to a variable y. Simply put, we are saying that y is a function of x. So here y is the dependent variable and x is a independent variable. And also we talked about average rate of change. So the average rate of change is given by, so we need to calculate the value of the function at x equals to b minus the value of the function at x equals to a divided by final point minus initial point. So this gave us the average rate of change. So if we replace b with x plus h, then our average rate of change simply becomes f of x plus h minus f of x, and we're replacing a with the variable x. So this is divided by h. So this is the average rate of change, and if we take the limiting condition when h approaches 0 of this average rate of change, f of x plus h minus f of x divided by h, this is what gives us the instantaneous rate of change. So this instantaneous rate of change is simply the derivative of our function, original function f of x. And this is the same thing as saying the change in y with respect to the change in x. So this is how we can also represent the instantaneous rate of change using dy over dx. We have been using dy over dx for some time now, but this is what it actually means, the dy over dx. This actually gives us the instantaneous rate of change of a particular dependent variable, which is y in this case, with respect to an independent variable, which is x. So what we will do today in this particular lecture, we will discuss few applications, and that's where the instantaneous rate of change becomes extremely useful case. So let us begin by considering the area of a circle. The area of a circle is given by pi times the radius squared, where r represents the radius. So we have the area given by a, so we have pi r squared. Now what we'll do, we will differentiate both sides with respect to radius r. So that means we have ddr of pi r squared. So pi is a constant, so this will come out of the differentiation. So we have ddr of r squared. Simply apply the power rule to r squared. This will be 2 times r raised to the power of 2 minus 1, or simply 2 pi r. Finding out the derivatives was extremely easy, but the thing that we need to do here is, what is the meaning of this particular formula of particular value? So dA over dr, so this is talking about the instantaneous rate of change of the area with respect to the radius. Meaning, so we will consider a circle with a radius of r. So for this particular circle, we have a certain area. Now, let's say after a certain period of time, this particular radius has increased. So that means we will get a bigger circle because the radius, new radius r1 is greater than the previous r value. And let's say we have another circle whose radius is r2, and in this case the value of r2 is even lesser than the original r. So in both of the case, in the first case, so this is our area 1 and this is area 2. So you can clearly see that area 1 will be greater than the original area A, whereas area 2 will be lesser than the original area A. The question is, by how much rate these area are changing when the radius r changes. So this is the meaning of an instantaneous rate of change. For instance, so let's say r was 1. In the first case, r is equals to 1. Then dA over dr, which is also referred to as the rate of change of area with respect to the radius. This is given by 2 pi r. So replace the value of r with 1. So this will give us 2 pi. And what is the area? So the area, unit of an area will be meter squared. We're considering standard units. Meter squared divided by meter. So this, don't cancel out the units. This is the meaning that this is the change in area per unit radius. So we can say that the area is changing with a value of 2 pi. So if we consider pi to be, let's say for calculation purpose, approximately 3. So this is approximately 6 meters squared per meter. So we can say that the area is changing with a rate of 6 meters square per 1 meter change in the radius. So let's say we consider a cost function. So let's assume x represents the number of toys. The cost of buying these toys is based on the formula 60x plus 0.01 x squared. Now we want to study the change in cost with respect to the change in number of toys. That means we want to find out dc over dx, the instantaneous change in cost when there is a change in number of toys. So that means we need to differentiate both sides with respect to x. So differentiation of 60x will be simply 60 plus 0.01 x squared. Differentiation of x squared will be 2x. So this gives us 60 plus 0.02 x. Now the question is, we have already found out the change in cost function with respect to the number of toys that is being bought. Now let's say xe represents 10. So that means 10 toys were bought. Then what will be the change in cost function? So dc over dx, so this is equals to 60 plus 0.02 times 10. So this will be equals to 60.2. So if we consider the cost to be in terms of dollars, then this represents $60.2 per toy. So this is the change in the value of the toys. Now if we consider that there are, let's say, 1000 numbers of toys, then in that case C prime of 1000, which is the rate of change of the cost function with respect to toys, will be given by 60 plus 0.02 into 1000. So we have 80. So this is $80 per toy. So you can say that when we increase the number of toys from 10 to 1000, which is almost over 100 times more, then we see that there is a increase in the price or the cost of the toys, cost of each toy. So that also increases from 60.2 to 80. The next problem, let's say, or let's consider a cube. So since a cube, it will have equal layer edges. So this is x, this is x, and this is x. So what will be the volume of this particular cube? So the volume of the cube, V, will be equals to x cube. Now what we want to study is the, let's say, the x value changes. That means the edges are changing. Now the question that we want to ask here, what is the change in volume when x also changes? So this is called the rate of change of volume with respect to its edges. So this will be equals to, so we want to find out ddx of, so replace v with x cube. So this is going to give us the value 3x squared. All we have done is apply the power rule. So let's say when x was equals to, we'll consider 1 centimeter, then the rate of change of volume with respect to its edges, this will be 3. So we will 3 with 3 centimeter cube per centimeter. Do not factor out the units. So it simply says that it's changing at the rate of 3 centimeter cubed per centimeter change in the edge. If x is equals to 3 centimeters, then dv over dx, rate of change of volume with respect to its edge, will be 3 times 3 squared. So this is 27. So we say that the volume is increasing at the rate of 27 centimeter cube per 3 centimeter change in the edges. So this is centimeter. So this is the meaning of the instantaneous rate of change.